schedule. Now we have memory overcommit for overcommitted admins. So I'm Jonathan Davies. I work for Nutanix. I work on the Acropolis Hypervisor. And today I'm presenting work done by David Rabel. So today I want to talk about memory overcommit. I want to start by talking about what it is, what I understand by memory overcommit, some techniques for achieving it, and then I'm going to talk about how we at Nutanix are approaching this problem, and then I'm going to talk about how we have used simulation to rapidly prototype an implementation for memory overcommit. So let's get started by thinking more generally about overcommit. So everyone is familiar with the concept of having more virtual CPUs than physical CPUs on a host. And typically people understand what this means. You can fit more virtual machines on a host, but there may be a performance penalty. So the performance will be worse if the machine is overcommitted than if you have more physical CPUs than virtual CPUs. Not only CPUs, but we can also overcommit GPUs with virtual GPUs. We can overcommit storage, capacity using techniques such as thin provisioning, and network bandwidth can be overcommitted. So what about memory? Well, memory is a little bit different because VM memory is allocated from the host memory. So in this example here, I have 4 VMs that are completely using up all of the host's memory. So what do we do when we want to start the 5th VM? The host is full. But in some use cases, VMs will not necessarily be using all of their memory allocation. This is not true in all use cases, but there are certainly some VM scenarios in which there's a bursty workload where some of the time is spent idle and it's not using any of its memory. Or you maybe are familiar with the example of where a user, a person who wants to own a VM has said, I need 16 gigabytes, but actually you know they will only be using 4 gigabytes or whatever. So there are cases where memory overcommit can be useful. So in the case of this 5th VM, where does it go? If we need to, we should be able to find enough room on this host, because these VMs are not using all the memory, to start that new VM. And this can be useful to cope with unforeseen short-term capacity problems. So for example, we may have had a hardware failure in some other node, and we need to evacuate that host, get the VM started somewhere else. So we may have this short-term problem of needing to fit more VMs in than we would normally be comfortable with. So this is why we need memory overcommit. There are 3 common techniques for implementing memory overcommit, and I'm going to talk about each of these in turn. Firstly, there's memory hot plug or memory hot unplug. Secondly, memory ballooning, and thirdly, hypervisor paging. And I'll talk about these. So firstly, memory hot plug and unplug. This is where we are adding and removing virtual DIMMs, memory modules, to or from the VMs. So if we want to reduce the memory available to a VM, we take away a DIMM. If we want to give more memory to the VM, we give it back. But although adding memory to a guest is easy, removing it may be hard. The OS may be using the memory on that virtual DIMM, so you cannot just take it away. The OS needs to do some work, and maybe there's even no guarantee that it can free up that DIMM by moving pages elsewhere. So this is not always going to work for all VMs. At best, this is an experimental feature in some OSs, but certainly not available in all OSs. And there's no guarantee over timely release, if at all. So even if you say, please can I unplug this DIMM, how long will the OS take to say, okay, it's available now? And thirdly, the administrator with this kind of technique often needs to indicate what is a safe memory range that the VM can operate in. So what is a safe limit? How much memory can I unplug safely from this VM? And not only does this involve some amount of guesswork, the administrator needs to understand what the workload in the VM is, but also, this takes time and there's some effort involved there. And if the administrator gets it wrong, there's even more time spent fixing up the problem, working out why the performance of this VM is worse than it should be, and sorting it out. So that's memory hot plug and unplug. What about memory ballooning, the second technique? So this is a technique where we are reclaiming unused pages from a running VM by running a special driver in the VM called a balloon driver. And it's called a balloon driver because imagine the idea of inflating a balloon inside the guest, and it's allocating memory pages from within the guest OS, but then it's, behind the scenes, giving that memory back to the hypervisor. So from the point of view of the hypervisor, although the VM still has its full memory allocation, we've actually got this extra memory. So it's as if there's this extra memory off to the side that we can now use for running new VMs in. So what are the issues with this? Firstly, it does require this special balloon driver. So not only is there something else to install, potentially in a VM, but we also need to trust the VMs. We need to trust that the VM will cooperate. And you can imagine a malicious guest having a variant of the balloon driver that doesn't perform or doesn't behave as we want it to. Secondly, if you do a VM reboot, the balloon is reset and doesn't have any pages allocated. That's okay. But if you are rebooting many guests at a similar time frame, then suddenly you've lost all that additional memory that you thought you had, and you're in an out-of-memory situation, and all kinds of problems will occur. And just as before, there's no guarantee over a timely release of memory. When you ask the balloon driver, please can I have some more pages, please? It may take some time. And just as before, there's some admin effort, maybe some guesswork involved here to configure this. So the third technique is hypervisor paging. So paging is a familiar technique, just like what we have in a bare metal operating system, where we're paging to a swap device. So we have the virtual memory and we're paging that to a swap device. Here we are paging the VM's memory to a swap device. So we have some backing store that's probably very large compared to the host memory, and we can take the idle pages, the pages that haven't been used from those VMs, and move them out to this swap device, and then hopefully we've got enough room to start that new VM. The problems here are performance. Performance is a big problem here because this swap device is likely to be very slow compared to memory, probably orders of magnitude slower than memory. So when we get it wrong, and when we page out something that we later need to page back in, the VM's performance will be impacted. So it's slow to swap pages back in when needed. And secondly, it does require a paging infrastructure in the hypervisor. So not all hypervisors have this. This is the KVM forum. So we have Linux as our host. And so we have a paging infrastructure, but that's not the case for all hypervisors. So that's the background. Let me now talk to you about the approach that we've taken at Nutanix to implement memory over commit. And I'll start by talking about our design goals. So what are the things that we wanted to achieve with this design? So firstly, automatic sizing. The title of this presentation was Memory Overcommit for the Overcommitted admin. So if we can do automatic sizing, then it takes that pressure off the administrator to do these calculations, keep an eye on what the VMs are doing. If we can get the VMs at the right size automatically, then we've made someone's life a little bit happier. We want it to be OS agnostic. We do not want to rely on any special features that the OS may or may not provide. We want this to work for any guest. We wanted it to be agentless, so we don't want to rely on the cooperation of some agent or special driver inside the guest. We wanted it to be fair, so there's no way for an uncooperative, or there's no way for a guest to be uncooperative. There's no way for it to hold on to memory that we want to remove from it. And it isn't really a word, is it? Disableable. We want this to be disableable. We know this isn't, memory overcommit isn't for everyone. It's not for every use case. There will be some VMs that we really don't want to reduce from their static allocation. So we need a way of selectively configuring which VMs have overcommit enabled and which ones have it disabled. So we want to allow a mix of VMs that can be squeezed and VMs that are not squeezed. So with those goals in mind, this is the approach that we chose. So there's two things I want to talk about here. The approach we've chosen is to use hypervisor paging, the third of those techniques that I described earlier, and to use feedback from the system to automatically size VMs. Let me talk about some of the pros and cons of those two approaches. So with hypervisor paging, as I said, this is straightforward. We have all the infrastructure already in place, and this is not to be taken for granted. With hypervisor paging, it is out of the control of the VM. The OS cannot do anything about this. If we as the hypervisor want to take away memory, we can do that, and we don't need any cooperation from the OS. We don't need any cooperation from any in-guest agents. There are some drawbacks. This won't work with VMs that use PCI pass-through because the IOMMU is not plumbed into the swap mechanism. And similarly, we cannot use memory allocated from the huge TLBFS, which is what we normally do on the Acropolis hypervisor. But again, that's not plumbed in to swap in the same way as the standard anonymous memory is in Linux. So we want to use feedback from the system to automatically size VMs. So this means no guesswork, no manual configuration for the admin to do. And if we get this right, we can minimize the amount of swapping needed. So that was critical. One of the drawbacks from hypervisor paging was to try to minimize the amount of swapping activity that's going on. So if we can minimize that by using the feedback from the system in the right way, then hopefully we can mitigate that potential problem. So let me get into some of the details. So we use C groups to control the paging. For those who are not familiar with C groups, this is a Linux concept to control the resources available to a particular process or set of processes. So the way we're using C groups is that each VM sits in two C groups. One is unique to that VM, and this is the C group that we will be using to control the memory that we are currently giving to that VM. So there's a parameter called memory.limit in bytes, and we can control that variable to control the memory size of that VM. So I'm saying we're putting the VM in the C group. What we're actually doing is putting the QEMU process in the C group and any other processes that are needed for the running of that VM. In our case, in the Acropolis hypervisor, we also use a separate process via the vhost user protocol, so that process will also go into the C group. The second C group is chosen based on whether the VM is one of the ones that we want to be overcommitted. If we have overcommit enabled on that VM, then we put it in the host-wide C group with swap enabled, and if it's one that we want to disable overcommit with, we put it in the C group with swap disabled. And we control whether swap is enabled or disabled with this memory.swappiness parameter. And we use a per host swap device for all the VMs that are in that C group with swappiness greater than 0. And just an implementation detail, we also, what's not drawn on this diagram are all the other components on the host that are responsible for the virtualization platform, such as the networking components. And if you're in the Acropolis hypervisor, we use the Open vSwitch, which is a use space process. So we have to be a little bit careful if our swap device is accessed over the network, that we don't swap our user space process responsible for networking out to the device. You can tie your brain in knots by working out what happens if that's the case. So how do we achieve automatic VM sizing? So I'm introducing the concept of a squeezer daemon that will be maintaining an estimate of each VM's working set. So the working set you can think of as the pages that this VM is actively using. So the squeezer daemon will be responsible for monitoring a VM and estimating the VM's working set size by observing the major fault rate from the QEMU process and the other processes that may be responsible for that VM. So if we look at the major fault rate for the QEMU process, if we have a low fault rate, then it means all is good. We've probably got a size for our C group that is bigger than we need. So we can actually at that point reduce the estimate for the size of the working set. On the other hand, if we have a high fault rate that we're observing, then that means we've squeezed that VM too much. And QEMU is protesting, and it's paging in this, these pages that are needed by the VM. So at that time, we realized that we've squeezed too much, so we increased the estimate of the working size. So we have this feedback cycle because then the squeezer is setting the VM's C group memory limit to the value of that estimate. So we have this cycle where the squeezer daemon will set a particular value for the C group's memory size. The VM will then respond in its behavior. If we set it too low, then the VM will respond by complaining, and that will be visible and observable by the QEMU major fault rate increasing. And then the squeezer daemon sees that and then responds. So we've got this nice feedback cycle. So this is good for automatic sizing. It's just as an aside, it's interesting from a control theoretic point of view that the QEMU major fault rate will only give one side of the story because it can only quantify over squeezing, and it won't tell us how much we've under squeezed. If the VM is too comfortable, if we've given it more memory than it needs, the fault rate will just be 0. So that's a slight subtlety that we'll come back to in a minute. So let me try and explain this with the help of a graph. If we hypothetically knew the size of the working set, if that was possible to measure, imagine that we could do that, and we have the orange line here showing the actual working set size for a VM undergoing some workload. Then we're trying to estimate that as best as we can with this green line, and we're doing a good job of estimating it at the start, but then at this point here, the working set is increasing, which means that the VM is asking for pages that we don't currently have present in memory, in host memory. So at that point, the fault rate will be going high. So the squeezer daemon will say, oh, okay, I've squeezed this VM too much, so it increases the estimate. All is well for a little bit longer, but then the working set goes up again in this example, so the same thing happens again. And then we're all good, and the squeezer daemon is happy, the fault rate is low, and then it may get so low to the point that it can actually try reducing the estimate here. Maybe it goes on for a bit longer and then reduces it again. And we're constantly maintaining this estimate. And the other thing to notice here is that all the time here we're below this dotted blue line, which is the static memory allocation for the VM. So anything below that means we're saving memory, and it means that we have the potential to run extra VMs or do what we want to do on the host. So this all sounds good, right? Well, there are some problems. As we've said before, we need to avoid paging as much as possible. Bringing pages in from swap is slow. It will impact performance. So this is a pathological example here where we've got a kind of cyclical workload where the VM is actively using some pages for some time and then has a bit of a rest, but then starts using them again, and then has a rest and starts using them again. So in this example, if we're following the shape of that working set too closely with our estimate of the working set size, then we're actually making some bad decisions, or decisions that have the appearance of being bad with the benefit of hindsight. We can see here that these pages, we do not want to put these out onto the slow swap device because soon after we're actually bringing them back in. So that was a bad decision to squeeze there. And there's another problem. The problem of hosts getting over full. What if you've got several VMs running and they all suddenly start this additional workload? They all increase their working set at the same time. If that's the case, then we get to this horrible situation where the sum of the VM's working set, their true working set that they're really trying to operate on, is greater than what we have available on the host. So the host is truly overcommitted here. This is really not good because all memory accesses, a lot of memory accesses from these VMs will be requiring pages to be pulled into swap, and then this will be replacing others. There'll be a lot of I/O and a lot of latency in just performing whatever workload the VMs are doing. So VM performance is necessarily impacted. We also, at this point, are unable to continue to compute estimates of working set sizes. Well, if we're lucky, we may be able to mitigate this if we have capacity somewhere else. We can try migrating VMs off to an underloaded host, an undercommitted host, but that's not always going to be possible. So we really want to avoid this scenario whenever possible. And one of the potential solutions to these problems is that we can try tracking long-term trends. So coming back to this cyclical VM example, well, what if we just were a little bit more conservative with when we start squeezing it down again? Even if we think the working set has diminished, maybe we still keep the C group a little bit higher, just in case it starts to need those pages again. And you can imagine extensions to this, such as tracking the highest estimate seen in each hour of the day, or in each hour of the week, or each day of the week. You can imagine that there are many VMs in which that kind of workload follows a pattern according to the clock. So that's a summary of the design approach, the kind of high-level design we've got for this memory over commit system. Let me now talk to you about how we went about prototyping and implementation of this, and we used the technique of simulation to help with this. So the question we have is, how can we evaluate a squeezing algorithm? So we're getting into the mindset of the squeezer daemon. What does it do when it sees the QEMU fault rate increase? By how much does it change the C group's memory limit? When does it change the C group's memory limit? Does it wait? What about this long-term estimate? What length of time window should we use? There's all kinds of questions here, lots of different parameters and basically numbers and things that we need to choose when we're implementing this squeezing algorithm. So the question we have is, how can we find an optimal squeezing algorithm? We want to have one that works well for our customers. So the solution we have to this is to use simulation. And the simulation will aid rapid prototyping. So it's a three-step process. Firstly, we have monitored real guest memory usage patterns under real-world workloads. And I'm going to be giving you some examples of that in a moment. From that real-world data, we can then construct a model that simplifies and summarizes this workload. And this enables us to quantify the impact of a particular squeezer algorithm on a VM workload. And then thirdly, if we then have a simulator that can simulate the behavior of the Linux memory subsystem, we can then rapidly evaluate different squeezer algorithms and see what impact they have on VM performance, and see by what extent they're able to squeeze down the VM's memory. So let me talk about these three things in turn. We'll start with monitoring. The way we've done this, to monitor the workload of real-world guests, is to use a feature of recent Linux kernels called idle page tracking. So if you follow the breadcrumbs from various files in the proc file system, you eventually can get to this file syskernel page idle bitmap, in which each bit of this file corresponds to a physical page on the host. And the bit is either 1 or 0 depending on whether it has been accessed since it was last reset. So what we can do when we're trying to monitor VMs is to reset those bits, and then so we can actually write to this file to set those bits, and then you read from the file a short period of time later and see whether the bits have fallen to 0. If the bits were cleared, then it means that the page has been accessed. So in this way, we can keep track of which pages are actually being accessed under a real-world workload in a VM. So let's look at some real examples. So the first example here is a git clone, and I'm in a Linux VM, and appropriately enough, I'm git cloning the Linux tree. So I'm sure you're all familiar with git clone. We've got these receiving objects, receiving deltas, phases. Let me now put that in the form of a picture based on the data that I've got from this idle page tracking system. So the whole thing took just over 100 seconds. I've got time on the horizontal axis. And on the vertical axis, we have the PFM, which is the physical frame number. You can think of that as an index of the page on the host, the physical page on the host. And I've actually grouped them here into superpage-sized chunks for clarity. The brighter, the warmer colours indicate pages that are accessed more frequently. So, we could spend a lot of time looking at this. It's a very interesting graph. There's a lot of, this tells us a lot about what's happening under the covers in Git, even if we don't know how it's implemented. And in fact, you can quite clearly see the different phases here of receiving objects, receiving deltas, that kind of thing. And actually, Git clone is quite a memory-intensive workload. There's a lot of things that need to be done in memory in terms of being able to deliver this file system. So this is one way of viewing the data. Let me flip it around. So here I have time on the horizontal axis. Let's now make time the color axis, if you want to call it that. And now what I've done is I've put every single page as a pixel in this diagram. So now on the horizontal axis, we've got each of the pages within those more granular chunks. So each pixel on here represents a page. It's a 4 gigabyte guess that I'm using, so there's a million pages in total, each of size 4K. And this tells us a lot about what's happening. It's interesting to see these horizontal stripes. This suggests that Linux is good at using superpages. But there's also a lot of black regions, and regions with the sort of darker colours. So this is interesting when we are thinking about whether we can squeeze this VM. If I try and summarize this in the form of a simpler graph, what I've done here is I've taken each of those pixels, I've sorted them by their color, the number of accesses, and I've plotted them here in this kind of histogram. So we can see that there's a very small number of pages that have a lot of accesses, but then a lot of pages fall into this category here, and it's relatively smooth. But then there's a lot of pages that are really accessed very infrequently, or maybe even not at all. So let's keep this in mind. Let's move on to the second example. So we've got our Git tree. What's the next thing? We build it. So not for the first time today, we've got an example of a kernel build. And what does this look like? Well, again, a picture paints 1,000 words. You can see from that better than I can describe what's going on. I guess the interesting thing is towards the end, it took a couple of minutes overall for me, towards the end is where you're doing all the final linking, and there's obviously a lot more interesting memory activity happening at that point in time. If we flip it around and go to our bitmap, where each pixel corresponds to a page, you can see here that there's a lot of darker colors. It looks like, again, this might be a VM that could be squeezed without too much performance impact. If I summarize it again on the same kind of graph as before, we see perhaps even smoother access pattern than what we had before. And again, we note that there are a large number of pages that are not accessed at all or very infrequently during this workload. So we've had a couple of Linux real-world examples, the git clone, the kernel build. I wanted to have an example from a Windows VM. So I did a lot of research to find out what the most common workload in a Windows VM is. So what happens when you're watching a video on YouTube? Well, here's the answer. So again, our idle page monitoring shows us the page access pattern, and this is the bitmap. You may be interested to observe that here we don't see the same kind of horizontal stripes that we saw in the previous examples, and I'll leave it as an exercise for you to decide or work out whether this is because it's Windows or because it's a different kind of workload. But again, the important thing I want to highlight here is the darker regions. So there's a lot of pages here that are not touched or touched very infrequently during this cat video. So we have, again, a very similar shape of graph. It's maybe a little bit tighter, so even more unused pages here. This was obviously a pretty gentle workload for this VM. So we've got these three examples, these three real-world scenarios where I've got real data, and I've tried to summarize it into this form. Can we build a model from this that we can use for our simulator? Well, all of them have very similar shapes, and I'm proposing that we can model this by firstly splitting our pages into two sets, the used pages and the unused pages, and then for the used pages, we can select pages that our workload is using by using a normal distribution. For our unused pages, we don't touch them. If we're interested in modeling variation over time, we saw with git clone and the Linux build that interesting things were happening at different points in time. We can model that variation by changing the parameters of the normal distribution or changing the ratio of unused and used pages. So when we have our model, we can then give it to the simulator. So what we need is a simulator of the Linux memory subsystem. And I have one right here. So we've created something called psim, and you can find it on GitHub and have a look at it, fork it, contribute to it, whatever. And this simulates a VM performing a workload and measuring the amount of work done in a given time. So this is how it works. It's a discrete event simulator. Every simulated tick, the workload that we're trying to run with the simulator determines which page a vCPU accesses. If that's already present in host memory, then it's all good. It can access it immediately. But if it accesses a free or unmapped page, that incurs a minor fault, which then blocks the vCPU from doing work for a short period of time. If it accesses a page that we have paged out to the swap device, then it incurs a major fault, so it blocks the vCPU from doing work for a prolonged period of time, related to the latency of that swap device. After the vCPU has accessed the page, it then does a unit of work on that page. And we can use this concept of a unit of work to then see over time how much work the vCPU is able to do in the presence of the memory being squeezed by a squeezer algorithm. But we've also got the Linux memory subsystem behavior being modeled, and that's happening in the background. Periodically, we are scanning memory to form a notion of active or inactive lists according to the pages that have been accessed since the last scan. And inactive pages are then candidates for paging out if the number of allocated pages exceeds the C group memory limit. So I've got a few examples that I want to show you of squeezer algorithms that we were prototyping to try and understand their behavior. So I've chosen a particular workload here that I'm going to be using in my next few examples. This is just one example. You can come up with any number of examples of workload, but for illustrative purposes, this is the one I'm going to be using. It's an alternating pattern of accessing using this normal distribution model, first by only using 50% of the pages, and then using 75%, and then alternating every 100,000 simulator ticks. And we're going to run the squeezer algorithm every 1,000 ticks. So what that does is that gives the squeezer a chance to change the C group memory limit once every 1,000 ticks. So, what does the simulator show for that workload? Let's start with the simplest squeezing algorithm that you can imagine, which is static squeezing. So I'm simulating here a guest of 128 pages. I mean, the units here are arbitrary, but 128 pages, and we're going to squeeze it at 50%, which is 64 pages. How does it respond? So in this case, all is well for the first 100,000 ticks, but then this blue line, which is a measure of the fault rate, that starts to rise after 100,000 ticks, and the fault rate is is quantified by the right-hand axis. So between 100,000 and 200,000 ticks, this memory limit of 64 pages was just too tight for this workload. We're now in this second period of where 75% of pages are being used. And then it gets a bit happier again between 200 and 300,000. and then it goes back to the bad case. So whenever there's faults, this is bad. Remember, fault means bad with effective VM performance. So the simulator tells us that with this particular simple squeezing algorithm, well, we've saved 50% of memory. So in one sense, that sounds good. We've saved a lot of memory that we can then potentially use for other VMs. And the total work done was 87.1%, because the simulator tells me we did 436,000 units of work out of a total of 500,000 units of time. So, okay, it's a start. But obviously this is not the kind of squeezing algorithm that we want. So let's try doing something a bit more intelligent. What about automatic squeezing by reducing the secret memory limit by 1 page, or increasing it if we have less or more than 2 major faults since we last ran the squeezer algorithm. So we can see here a slightly more interesting fault rate, and we've managed to achieve 92% performance, and the average memory limit here was 53.8% of the static allocation. So it's maybe a little bit better than that static squeezer. But there's some problems. We notice that there are these sustained periods of faults that go on for quite a lot of time. And you would say, well, maybe we can be quicker to respond when there's a burst of faults. So let's try that. Let's try proportional squeezing, where we're reducing or increasing the secret memory limit by the number of major faults in that period. So now we're able to respond much quicker to that spike in fault rate. So although we did have those faults, we then bumped the limit up very aggressively, and then the fault rate then fell down very quickly. So that's good, we solved that problem. So we're now up to 95.3% performance, and our average was 56.2. So maybe we were doing a little bit better than we were before. One of the other things we tried was using an infinite impulse response filter, if you're familiar with control theory and IIR, to smooth out the recent fault rate, because we noticed that previously it was quite bumpy, and maybe it was too bumpy. So if we can try and smooth it out, we're now using a weighted average of the number of faults since the start. And actually it turns out from the numbers that this isn't quite as good, because we're now maybe smoothing out a bit too much those times when we do want to aggressively increase the memory limit. But perhaps we're trying a bit too hard. Maybe we're just trying to get a bit too close to the VM's working set. So we could imagine a different kind of squeezer algorithm that is much more conservative. So in this particular algorithm here that we run through the simulator, we start with a hard squeeze. So we squeeze it down aggressively until we get the very first page fault. And at the time we get the very first page fault, we then back off, give it a bit more memory. Every time we get a page fault, we give it a bit more. And it's only when we have a prolonged period of time when there are almost no faults that we can then start just testing the waters and seeing whether we can squeeze it back down again. So it's quite a different shape of graph this time. The average memory limit is now 80%. So now is it good or bad? You decide. We're now not saving as much memory as we did before, but on the other hand, you can still say, well, we are saving 20% of memory here, and potentially if we have enough VMs here that are all saving 20%, then we've got room to start those extra VMs that we want to start. And all the while, we're actually attaining 99.4% performance as reported by the simulator. So this is barely imperceptible to the guest. So we've saved memory, and the user can barely notice that anything has happened. So that brings me to the end of the examples I've got time for now. Let me just summarize the main points. So memory overcommit is beneficial for some use cases and workloads. It's not a panacea. We know that there are some workloads and use cases where we don't want to do this, but where it is useful, hypervisor paging is a good technique because it doesn't require guest cooperation. We don't need to trust what's running in our guest. Automatic VM memory sizing is beneficial because it can avoid administrative effort, guesswork, needing to fix up problems. We've shown that a squeezer algorithm can be evaluated using simulation that's based on real-world data that we've monitored from real guests. And finally, We believe that a good squeezer algorithm can maintain good levels of VM performance whilst squeezing VMs close to their actual working set. That's all I have for you. Thank you. Any questions? So, microphone and then thank you.
So first question, you said you made the simulation based on normally distributing faults, except that the graphs you were showing before with the accesses versus the didn't look like normal distributions to me at all.
So they certainly change over time. So we can essentially change the parameters of our distribution over time to change how it's using the memory. Absolutely, you're absolutely right. This is only a model, and it is approximating the performance.
Right,
we wanted something simple to feed into the simulator.
Normal model rather than a sort of exponential fall off.
Absolutely,
looks a lot more close to what you have there.
Let's do it. You know, the normal distribution here is just one example of a model. We can. The good thing now is we have this simulator. We can look at different models and very rapidly look at different squeezer algorithms and see how they perform. You know, it's dead easy to implement something that's not a normal algorithm, a normal distribution, and see how it performs. So yeah, good point.
Yes. Well, yeah. Okay. Well, the other question is, you use the Datalog data essentially to generate your simulation model.
Yeah.
Why not use that directly to?
Good question. The main reason is that we need to simplify it a bit if we want our squeezer algorithms, our simulator to run in a short time. So, you know, I'm talking about simulating hundreds of thousands of cycles in the VM. Essentially, we could try and feed that real-world data in, and I'm all ears if you want. You can go and implement it yourself. Thanks.
So basically what you're simulating is one VM. And I mean, whenever you talk about memory overcommitment, usually people say avoid swapping by any means.
Yep.
And did you ever try to simulate multiple VMs? Because then you have a limit of I/O throughput and your figures will look completely different. Did you ever try simulating something like that?
That's a really good point. And yeah, what you could actually imagine is if you have a model of the I/O going to the swap device, you could even model that in the simulator. And if you have multiple VMs, then yeah, you could then penalize VMs even more if the swap device is busy. Absolutely. So yeah, this is a great topic for future work. It's not something we've done.
So you haven't done it yet?
Not done this yet, no.
Okay, and the second thing would be a question. Do you assume that your host is constantly under memory pressure? Is that like the typical setup? Like a hypervisor would be constantly under memory pressure and it would be constantly, for example, evicting everything from its page cache.
So for the VMs that we have marked as, yes, please overcommit these, then yes, the squeezer will be trying to maintain some estimate of the working set. So it will always be putting some pressure on the VM because that's the way that it can
I mean for the hypervisor.
For the host, I don't. There's no need to assume that.
So I mean, in your typical setup that you would imagine, your page cache of your hypervisor would not be affected by whatever is going on in there.
Oh, you mean in terms of other things using the same device?
No, just general. I mean, you have a page cache for your disk or whatsoever, and it might get important at some point in time that you maintain the page cache in your hypervisor. And if you have some constant memory pressure in your hypervisor, that's what I'm asking, then you might simply evict it all the time, which might also result in some bad performance.
Yeah, it would if we're caching I/O. Yeah. Okay. In our case, that's not a problem because we're not using the page cache for storing I/O.
Okay.
So
Where am I looking? Hello?
So you mentioned about the squeezing algorithm which you are using. I'm wondering, does this squeezing algorithm monitors the idle time as well? I mean, for example, if the working set which you have defined is like 2 GB and the guest is using maybe 1 GB or is idle but host is kind of under memory pressure, so does this squeezing algorithm will monitor that particular situation or scenario or not?
You mean monitoring the vCPU activity?
Whether it is idle, I mean, if it's idle, then you can actually take
Absolutely.
one.
Yeah, that's a great idea. That's another input that we could feed into our feedback cycle. Yeah, good idea. Someone with a hand up at the back?
I think.
Or we're okay.
You can read also.
One question? Or at a time?
Other than.
At a time. Come and talk to me afterwards. Thank you.